Fernando, this is my favorite song. You know which song, Fernando?
Yes, I know it. Yeah.
Which orchestra? Which team? ABBA, right?
ABBA, yeah.
That's one of their famous songs, besides Mamma Mia and Dancing Queen, right?
That's it, yeah.
Okay. So, anybody has questioned what I said, or have opinion one way or another? You know. Oh, okay. Maybe since I have you all, I'd like to now make one other point, and we'll get into another part when I want to discuss. You see here, in a switch mode conversion, we have by definition, we are driving a transformer the square wave. Because why? We start with a DC source in DC to DC converters. We interrupt it. So we, by definition, have a square wave voltage drive, right? And then the current. So that's one thing. But does it have to be always that way? No. And I'll show you what I called and invented 5 years ago, 2018. Now it's what, 2018? Oh, no, 2018, my patent expired. Not patent, my exclusive rights I gave to Infineon. But 2013, I invented a converter which I call the Chukpak 2. And what it does is a square wave voltage drive, which is used. You see the difference in a transformer, 60 Hertz transformer, there is no regulation ability, right? In fact, that was a big problem with the 60 Hertz utility line. When in the middle of the day, a lot of people want to use electricity, turn on air conditioning, turn on the washer and dryer and so on, and suddenly you use a lot of power. And what happened? Utility voltage drops. And utility line has to automatically make up for that loss. So what do? Back in Serbia, they have a thermal power plant in Kolubara or whatever. And they said, oh, turn on generator number 3 or number 4 to make up for to get extra power loss. The utility had to maintain the balance to keep the voltage constant, because the whole utility is based on transferring 110 volt fixed voltage in the United States and 220 volts in Europe. So therefore, the utility was charged with the fact to do that. What happened in China? I don't want to put them down, but in China, typically utility companies wouldn't guarantee the voltage, and it could drop 30%. But in the United States, if the voltage drops below something, then the utility company has to guarantee that voltage. Now, if you have a switching converter, you have one more option. You can regulate it. So therefore, transformer has an additional point that it can regulate, and it can provide as a fluctuation of power is it can keep the voltage constant, but regulate it even though it changes 20-30% with the demand going up and down. That's one thing. The other, does it have to be square wave voltage and square wave current? No, it doesn't. I showed you last time Chuk converter. That was the first one, which was true AC transformer, provided both square wave voltage and square wave current, like I just described here. But what kind of waveforms you present on a transformer? It depends what you put around it. And that's what the people didn't understand. And it took me 20 years, and I still have to teach them and say, no, all these smart guys who claim, oh, transformer is nothing. Dr. Chuk, why insist the flyback transformer is not a transformer? It's just 2 pieces of wire on a cord, magnetic cord. Of course it's not. How transformer depends on all the external circuit connected to it, how the switches are connected, how the capacitors are connected, and any inductors that you have which you really don't want. And that's another subject. You want to make a transformer which is just like a transformer and hopefully capacitors and switches around it. But can you make it? Can you make it with the different waveforms? And why would you want to do that? Okay, so let me explain that here. You know how the 60 Hz transformers are made?
Bogdan,
Yes.
you are not sharing the screen.
Oh, I'm not sharing the screen? Okay. So, yeah, because we are talking exactly. I got excited. Now you see it. Okay. So now 60 Hz transformer. It's huge power, megawatts and so on. We have the real transformer. Not only has a magnetizing inductance, but it has a flux, self-enclosed and enclosed flux here. So the actual real model has a magnetizing inductance, leakage inductance on a primary, and leakage inductance on a secondary. Okay. Is this any, I presented you a simple model describing if these leakages are not there. And how would you do that to have these leakages as small as possible? You'll make a primary and secondary right at the top of each other and coupled such that there is no minimize the leakage and maximize the coupling. The primary is fully coupled to secondary and leakages are minimized. Do you know that the 60 Hz transformer, or for that matter, 400 Hz for a chipboard, etc., they actually have intentionally inductors, primary and secondary winding on separate legs. You know, if you have a core. Like this, then you will make it like UI core. You will make it winding here and winding here. This will have a large leakage because the windings are separate and they have a large leakages. And in fact, in 60 Hz transformer, they don't even care how much leakage is on one side and how much leakage on the side. All they care is what is the total leakage. When you reflect this on the primary side and sum these two leakages, you have total leakage. And you know that they want to have this leakage to be 10% to 20% of the magnetizing inductance. They want a leakage large. Why would they want to do that? What if happens on this winding here? You have a winding with the insulation, insulated wire, and insulated wire breaks down and makes a short. What's happened when there is a short on the transformer? You don't want to have a short on 60 Hz transformer, especially at megawatts. You're going to have a mega currents, and something is going to explode, right? So what you're going to do? You want to have this transformer to have high leakage because it will have a very high inductance, but once you short, this will have once there is a short, all you're left with the inductance, leakage inductance of this structure. So you want to have leakage inductance not flat, square, but reasonably high, because you have this circuit breakers, and circuit breakers need a few seconds to shut off. So you want to have that leakage inductance to limit the current during this few seconds so you can shut it off, right? Then there is this other problem. Do you know that a transformer like this, it has you don't like a resistor, right? You don't like resistance in it, okay? Because it causes copper losses. But what happens with the real transformer? A real transformer will have a remnant magnetism. When you have zero current, you have a still remnant magnetism. So what happens when you start a converter, when you start 60 Hz transformer, it may start from here. And because it didn't start from negative to positive, but it started on a positive remnant magnetism, which is much closer to the saturation. So in the first cycle, you may actually short the core, right? Go in saturation, because you start here rather than starting from here and back and forth, right? Because you didn't start from negative saturation, negative here or even this part, so you had time to come back. And what happened? Nothing will happen, because that resistance in the coil will simply say that it's an automatic feedback. So if you have too much voltage flux here, well, you'll draw the current, and this current will reduce the drive in a positive direction. So you see, it's a self-directing. Positive feedback essentially makes a core may start with remnant magnetism and go eventually settled in a symmetrical way. So when you say then you would have a real problem if your transformer has a zero resistance, right? Let's say it's made out of superconducting coils, right? Then there is no such a thing like this, and it will definitely saturate. So you have to have active means. And one of my students, Alan Kuconi, was as part of when he was my PhD, my master's degree student, worked with me on research. He came up with the idea how to just basically you have magnetic core and pod core, and at that time I worked on my integral magnetics, and I said, okay, you put your power windings on a core with a transformer, primary and secondary, and then put an orthogonal windings to the center of the pod core. And you know what he found? We would expect that this will be inductor windings, so you would have a transformer flux and inductor flux. And I was hoping that, or actually, reason why I suggested it, that we could have a resultant flux, which is one which saturates the core, so we could actually cheat and have 70% of the possible flux dedicated to transformer and 70% dedicated to inductor, and cheat to have both inductor and transformer using the same core with a maximum flux density 1 Tesla, but each one having a 70.7 Tesla in each direction, get more done with less. But then when he made this test for myself to look at it, he found out 2 orthogonal windings do not interact. But it turned out they did. And why? Another student of mine, Bill Politica, my PhD students, explained why this winding here will, even though it's orthogonal, ideally 2 fluxes would not interact. This winding will have an AC voltage, and the higher, closer to saturation, the bigger the AC voltage. You can use this as a sense winding, and if you drive a transformer in one direction, and like you started from here, driving in one direction, you can actually stop driving it in that direction because the sense winding will tell you how far you're close to saturation, and you will drive devices in opposite direction to drive the flux in the other direction. So there is an active means to really, for example, that you do it full bridge, half bridge, push-pull, to operate at the maximum flux capability without ever worrying that you're going to get into saturation of the transformer and use a maximum flux rate. Okay. All right. So let's go back. Yes, question?